We're going to talk about two special cases of antiderivative, and one of them we talked about it in the last video, one of the last videos about the e to the x function. If you take the derivative of e to the x, it's itself, and you need to take the antiderivative of it. Now, this elongated s, if you haven't come across it yet, it's an integral notation, which is the same as antiderivative of e to the x dx is e to the x back plus the constant of integration that we talked about, or part of that constant for the antiderivative. Now, what if, this is the first special case, all right? But what if you have the function 2 to the x, so instead of base e, okay, that special number, Euler number, you have any base that is not e, so 2 to the x. What would be the derivative in here? Well, the very first thing we have to do, we have to manipulate this expression so that we can actually do some maneuvering. And if you remember from the logarithmic unit, we can rewrite 2 as e to the ln of 2. And the reason we know that is that every time you have a log that is got the same base, so ln is a natural log with a base e. So another way of writing that is 2e to the log of e, base e of 2. When you have a base of this log is e, and the base of the entire expression is e, then the final value of the entire expression is 2, which is the argument of log. All right, so in this case it's the same idea. So now we're going to use this, and we're going to use the chain rule. Okay, now let's see. 2x, we're going to write 2x in terms of this expression. Okay, we already have 2 in here, so we're going to, instead of 2, I'm going to write e to the ln of 2, but this is to the exponent x, so that means I have to raise that to the exponent of x. Okay, and when I do that, this is the exponent of the exponent, power of a power, so this is one of the exponent laws. So this would be e to the x ln of 2. That is the value of 2 to the x. Now that we have this, we're going to use the chain rule to differentiate. Okay, and to do that, we're going to set u equals to x ln of 2. Okay, that means now our expression 2 to the x, by the way, that was the y function, right, is equal to e to the u. Okay, simple as that. Now that we have this, we can go ahead and take the derivative of e to the u. So e to the u, when you take the derivative of that, so d dx e to the u is e to the u times du dx. Okay, simple as that. That's the chain rule, and we know that that is true. Now that we have this, notice that we don't have du dx, okay, but we have this. All right, so we have u equal to x ln u, so we can go ahead and find what du dx is. So we're gonna say du dx is equal to d dx of x ln of 2, and in this case the answer will be ln of 2. Okay, so the ddx, so we're going to take the derivative of this right here, du dx of both sides. So we're going to say du dx is equal to ddx of x ln of 2, when the answer to this will be just the constant ln of 2, because of 2x is 2 if you take the derivative of 2x, 3x when you take the derivative of 3x is just 3, just a constant. Okay, so ln of 2 is just a number. Now we have that. Great. Now that we have this, we can go ahead and replace this part right there on top right here. This, now we're going to replace that with e to the u times ln of u, ln of 2, okay? And now we're going to go ahead and replace u with x ln of 2. So e to the x ln of 2 times ln of 2. That is the answer to that. But originally, what did we do? We replaced this 2 to the x with that e to the x ln of 2. So we're going to go back ahead and substitute it back to 2 to the x. All right. So now the final answer will be 2 to the x times ln of 2. And you can bring the coefficient in front, ln of 2 times 2 to the x. It doesn't really matter. But that is the derivative of 2 to the x. Okay, that is the long-winded way that I needed to show you this, but there is a reason that I did that. Now we can actually make this a general form. That means d dx of any exponential a to the x is equal to ln of a times a to the x. So we can make that observation now, and that is another special case. Okay, and now the last one is, now that we have this, we can prove one of these questions, and the question is this, which is going to lead to our third special case. We want to show that the antiderivative of 2 to the x is equal to 2 to the x divided by ln of 2 plus c. Okay, so it's very simple. We just have to go ahead and take the derivative of the second term, right? But before doing that, I just want to make sure that the notation is right. So this is what we're looking at. The antiderivative, which is the integral of 2 to the x dx, we want to show that is equal to 2 to the x over ln of 2 plus c. All right, so simple as that, and we just have to go and take the derivative of the right-hand side, and let's go ahead and do that, knowing that ln of 2 is just a constant. Take the 1 over ln of 2 outside, so 1 over ln of 2 is outside, and then d dx of 2 to the x plus d dx of the constant c. Okay, we know that the ddx of the derivative of a constant, that's 0, and that's not going to affect anything, so that's easy. Now we're going to go ahead and take the derivative of 2 to the x, but we've done this already in the example above. Okay, so the derivative of 2 to the x was right here. Okay, so ln of 2 times 2 to the x, right there, ln of 2 times 2 to the x. So here it is. So we have 1 over ln of 2 times ln of 2 times 2 to the x. Okay, and now that we have that, we can divide the ln of 2 and ln of 2, and the final answer will be 2 to the x. Now we can go ahead now and generalize this special case, that is the integral or antiderivative of any exponential function with the base that is not e dx is equal to a to the x divided by ln of a plus c. This is the other special case that I wanted to talk about. And a has to be greater than 0, and a also cannot be equal to 1. And it makes sense because ln of 1, that would become 0, and you cannot have a denominator with the value of 0, that would be undefined. And of course, a has to be positive value in this case, not negative value. All right, that is it. I hope this was useful. Check out the next video, and don't forget to do the practices, the practice, or the quizzes that I post, and make sure you check the answers as well, but make sure you do a review first so that you can check your own mastery. All right, until next time.